Hello guys, how are you all? Hope that you are doing good all. Okay, today we're going to continue our lessons with chapter 21, section 2, which is radioactive decay. Now, as we said at our previous lessons, that transmutation is changing of the identity of the atom. And this process is called transmutation. Now, this process actually goes for radioactive element, as we said, that elements that are above or below the stability band, which is the ratio between neutrons and protons. And as we said, if the ratio was over 1.5 or less than 1, that means that the atom actually located outside the stability band. So, how does the atom goes to transmutation? As we said also before, that could happen through radioactive decay, which is spontaneous disintegration of a nucleus into slightly lighter nucleus, accompanied by emission of particles or electromagnetic radiation or both together. And this radiation that exposed the plate was nuclear radiation, which is particles or electromagnetic radiation emitted from the nucleus during the radioactive decays. So the radioactive atom actually emits some particles or electromagnetic radiation to change to another atom or to be changed to another atom. Like, for example, uranium, which is a radioactive nuclide, as an unstable nuclide, undergoes the radioactive decay. Now, if we wanted to study the types of particles or emission that will be emitted from the protons, we can classify it within main 4 types. First one is alpha particle, as we see here, which is actually 2 protons and 2 neutrons. And because it is 2 protons and 2 neutrons, so the mass of it will be 4. So the atomic mass is 4, and atomic number will be 2, which is helium. And it is actually positively charged with +2 because we have 2 protons only with no electrons. So here we have to know that we wrote it as helium but without electrons. Okay, this is why alpha particles has +2 charge. And as you can see, it is almost 4 atomic mass unit, okay, because it is 4 nucleons. The other type is beta particles. As you can see, symbolized by beta, the Greek letter beta, with atomic number -1 and atomic mass 0. And beta particles actually, it is the electrons. Okay, and as you know, the electron is negatively charged by 1 charge with almost 0 mass, as you can see. The mass is very small, very, very small, that we negligate it. So we consider it 0 mass. The third one is positron, which is +1, which has the same properties of electron, but with a different charge, the opposite charge, which is +1. And the fourth and last one is gamma ray, which is a type of electromagnetic wave. So it isn't a particle at all, it's just type of rays. Now, let's talk about each one with some details. First, alpha particles. As mentioned before, an alpha particle is 2 protons and 2 neutrons bound together and is emitted from the nucleus during some kind of radioactive decay. And alpha particles are helium nuclei. And we said the nuclei because it is not an atom. The atom of helium contains electrons, but here we said helium nuclei because there is no electrons inside. And Alpha particle emission is restricted almost entirely to very heavy nuclei. In these nuclei, both the number of neutrons and number of protons need to be reduced in order to increase the stability of the nucleus. So here we are going to reduce the number of protons and the neutrons, both of them, to increase the stability for the nucleus. An example for alpha emission is decay of polonium to lead, as we can see in this nuclear equation. Polonium converted to lead with emission of alpha particle. And as you can see, the total atomic number for the products must be equal to the total atomic number of the reactants. So we have for the reactants, polonium atomic number is 84, and we have atomic number for lead is 82, and 2 for helium, so the sum of it will be 84. Same thing with the atomic mass. Atomic mass is 210 for polonium, and we have 206 for lead plus 4 for helium, so the total will be 210. Beta emission. Beta emission is an electron emitted from the nucleus during some kind of radioactive decay. And actually, you can ask the following question. How will an electron be emitted from inside the nucleus? Because we don't have any electrons inside there. All what we have inside is protons and neutrons. And the answer for that question is that the neutron itself converted to proton. As you can see here, if we have neutron, and the neutron is particle with a plus and minus charge, so it is a neutron. If a part of this, a neutron, this part, very small part of the neutron, split it from the neutron and took the negative charge with it, it will form the electron. So the rest of the neutron will become positively charged, which is proton. So in this type of radiation, when the beta particles are emitted from the nucleus, the number of protons will be increased. So the atomic number will be increased. Okay, so the atom itself will be changed to a new element with higher atomic number, but the atomic mass will be the same. As we can see here, carbon 14 goes to radioactive decay to form nitrogen, which is directly after carbon in the periodic table, as we can see here. This is carbon here with atomic number 6, and the element after carbon exactly is nitrogen with atomic number 7. And the next one is positron emission, which is a particle that has the same mass as the electron but has a positive charge and is emitted from the nucleus during some kind of radioactive decay. And the situation here is totally different from the previous one. So we have the proton, which is positively charged. Now, if a small part of the proton here split from the proton and goes out with the positive charge. So because it has a small mass, so it is just like the electron, but with a positive charge. So the rest of the particle, which is the proton, will become neutral because the charge is out with the small particle. So this is the neutron. So in this case, when positron emitted, the atomic number of the atom will be decreases, and the element will be converted to another element with less atomic number, while the mass will be the same. And remember here that The mass, we are talking about isotopes. So it is not a must that you must have the same mass as the periodic table. Because as we know, the atomic mass in the periodic table is the average of all isotopes for the elements. An example for positron emission is potassium converted to argon with atomic number 18, as you can see here, with emission of beta particles. Now, we have another process could happen actually in the radioactive elements, which is electron capture. In electron capture, an inner orbital electron is captured by the nucleus of its own atom. So, if we have, as we know, this is the nucleus with the proton, positive, and the neutron, negative. And here we have the inner electrons. If this electron is captured by the nucleus, remember here we are talking about the same atom. The electron will be moved inside the nucleus and it's gonna to neutralize the proton, and the proton will be plus minus. So atomic number will be decreases, and the mass, atomic mass, will be unchanged. Because the proton itself is actually counted with the atomic mass, so nothing changed for the mass. An example for electron capture is silver 47, silver isotope 106, capturing an electron to form PD 46, because the proton here changed to neutron, so the atomic number is decreases. Last one is the emission of gamma ray. Gamma ray, it is a high energy electromagnetic waves. So here we are talking about waves, we are not talking about particles, emitted from the nucleus as it changes from an excited state to ground state. Remember guys, in the earlier lessons, we used to say that usually if we have the main energy level is here, if we have an electron at this orbital, and the electron goes up to a higher energy level, it will absorb energy. And when this electron moves back to its main energy level, original one, it's gonna to emit energy. So emission of energy with the electron case is from the excited state to ground state. Same thing happened with the atom. When the atom changed from excited state to ground state, it will emit type of rays, which is gamma rays. So the emission of gamma rays is another piece of evidence supporting the nuclear shell model. This is how we can know that we have orbitals for electrons and orbitals for, or orbitals like inside the nucleus for the nucleons. And according to the nuclear shell model, gamma rays are produced when the nuclear particles undergoes transition in a nuclear energy level. So, and this is similar to the emission of photons when the electron drop to lower energy level. Now, gamma emission usually occurs immediately following other type of decay. So usually, gamma rays will be a friend for another type of particles. For example, if an atom releases alpha particles or beta particles, gamma rays will be released also and emitted with the alpha particles and gamma and beta particles. Just to remember, this is the electromagnetic spectrum figure. As we can see here, gamma ray is the last one with highest energy and highest frequency, with the lowest wavelength, and because it has a very high energy and a very high frequency. So actually, this type of radiation considered the most dangerous radiation from all of above, because penetrating ability for gamma rays is very high. It's able to penetrate skin and could change the DNA for the cell inside, which cause a lot of disease like cancer. So this is a brief for our lesson today. Okay, let's solve some example here. Let's start with, if we have ES 99 with 253 plus helium 2 4 will give us neutron 0 1, and the other one PM 61 with 142 plus a non-particle to form NB 60 and 142. Okay, and the first question, sorry. As you can see, neutron released, zero atomic number with mass. And so the total number here of the atomic number must be the same. So first the atomic number must be 101. We add 2 with 91. Now, we have to go to the periodic table, sorry, and see which element has 101 atomic number. As you can see, it is MD, Mendelevium. D, and the atomic mass will be the sum of this side 2, 5, 7, but here we have 1, so the atomic mass here must be -1, so 2, 5, 6. This is Mendelevium isotope. And the other equation, what do you think that we should fill in the blank here? Look at the atomic number, it is changed, decreases, and the atomic mass stays the same. So what do you think, what we have here? Remember that must be -1 in mass, in atomic number. So here we must have electron, as we said before, electron capture. Let's take another example, which is beryllium 4, 9 plus helium 2, 4 will give us plus neutron 0, 1. Remember that here, because here we have the atomic number is 6, so the atomic number here must be 6. And the total number here is 13. So here 13, but remember that here we have another one, so this one must be 12. Now go to the periodic table. You can see that carbon is the element with atomic number 6, so carbon. Third example, sodium Na22 plus unknown will give us neon 10, 22. So remember that here we must have 1 with 0. Now, here we are talking about what? We're talking about minus. So we are talking about beta particles or electron minus 1, 0. Okay, hope guys that you get it and you know how to solve the equation by making balancing, by make the equation balanced at both atomic mass and atomic number. Okay, sometimes you could have an equation that, like for example, this equation. For example, if we have Re 75 with 142 plus unknown, give us Re 75 with 142 plus H11. Now here, because we have same elements here, so the other element here must be equal to the one at the other side. So simply just H11. This is how we solve it. You just follow the change in the atomic number, and remember that the particles that we have is helium 2, 4, or beta particles with 0, minus 1, or electron plus 1 with 0, or we could have electron minus 1, 0. Now here, this one, it could be electron capture or releasing of beta particles. This is the difference. Now you have to fill the blank in the nuclear equation by one of these 4 particles to be able to determine the nature of the element that will be produced or react in the reactant site. Thank you and have a nice day.